This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 3, Lesson 9, Adhesives and Bonding. We've covered two great families of mechanical attachment, welded joints and bolted or riveted joints. This lesson adds the third, bonded joints. Adhesives behave differently from a bolt or a weld. They're strong when the bond is loaded in shear across its overlap, but they come apart early if the load tries to peel or pry an edge. This is the lightest lesson of the week. The handbook gives one table of adhesive strengths and one figure of design practices, and the whole point is that how you design the joint matters far more than which glue you reach for. Here's the problem. Two straps are bonded in a single lap joint and pulled apart with a 4 kilonewton load. The bond is 25 millimeters wide and overlaps 20 millimeters. Find the average shear the bond must carry, then screen the handbook's adhesive table to choose a chemistry that can hold it. Keeping in mind, the table lists room temperature test averages, so you still have to leave room for a factor of safety. One formula, one lookup, one design decision. Concept 1. Strong in shear, weak in peel. A bonded lap joint spreads the load over its whole overlap and carries it as an average shear. The load divided by the bond area, width times overlap length. That's where adhesives are strongest. The weakness is peel and cleavage, a load that pries the bond apart at an edge, and in a lap joint, the peel stress bunches up at the two ends of the overlap, which is exactly where it starts to let go. Strengths run across nearly 3 orders of magnitude between chemistries, but the overlap length, an end taper, and hybrid fasteners matter more than reaching for the strongest glue. Setup. The handbook's one adhesive table. It lists room temperature, lap shear strength, and peel strength by chemistry, and I've pulled 6 representative rows spanning the range, from pressure-sensitive tapes at the bottom up to rubber-modified epoxy at the top, nearly 3 orders of magnitude. 2 cautions are built right into the columns. The peel column is a force per unit width, in kilonewtons per meter. That's not a stress, so never compare it against the megapascal column. And every number is a room temperature test average, not a design allowable. One more pattern worth seeing. High shear strength does not guarantee high peel resistance. A plain epoxy is strong in shear, but poor in peel, while a rubber-toughened epoxy is good at both. Concept. Design the joint, not just the glue. The handbook's practices figure makes 2 points. First, load the bond in shear. Reorient the joint so the force runs along the bond instead of prying an edge. The figure flags peel and cleavage loads as poor and redesigns them into shear. Second, shed the peel that builds at the ends of a lap joint, and it names 4 ways: taper the overlap end, hem or fold the end to mechanically reduce peel, rivet or spot weld or bolt the end into a hybrid joint, or simply enlarge the bond area. Every one keeps the bond in shear and eases the peel spike at the overlap end. Solve. Size the bond, then pick a family. The bond area is width times overlap, 500 square millimeters. The average shear is the load over that area, 8 megapascals, about 1160 psi. Screen that against the table's averages. Pressure-sensitive and white glue fall below 8, so they're out. Cyanoacrylate, urethane, and the epoxies all clear it on paper. But those are test averages, so leave a factor of safety, call it 2, which lifts the target to about 16 megapascals. Now an epoxy is the clean choice, and a rubber-modified epoxy clears that across its whole range, while also carrying the best peel strength in the table. The raw number screens, the factor of safety decides. Traps. 5 ways this bites. 1. The table is test averages, not design allowables, so apply a factor of safety before calling a glue adequate. 2. Peel is a force per unit width in kilonewtons per meter, while lap shear is a stress in megapascals. Different quantities, so never compare the 2 columns. 3. High shear strength doesn't mean high peel resistance. Plain epoxy is strong in shear, but weak in peel, so reach for a toughened epoxy when peel is present. 4. Design for the right load. Adhesives fail in peel and cleavage long before shear, so orient the joint to keep the bond in shear. And 5. A longer overlap has diminishing returns, because the stress peaks at the ends. Taper or rivet those ends, instead of just adding length. Quick recall. Size a bonded joint by the average lap shear, load over width times overlap. Get strengths from the one handbook table, remembering the peel column is a force per unit width, not a stress. Follow the design practices, taper, hem, rivet, or enlarge the bond to keep the load in shear and ease peel at the ends. And because the table is room temperature test averages, always leave a factor of safety underneath. Our worked joints needed 8 megapascals raw, or about 16 with a factor of safety, which points to a rubber-modified epoxy. The golden rule: a bonded joint is only as good as its design. Next up, Lesson 10, Exam Strategy, and it closes out Week 3. Between them, these lessons have covered the 3 attachment families: welded joints, bolted and riveted joints, and now bonded joints, each with its own load path and failure mode. Lesson 10 pulls them together for the exam: how these problems are framed, how to spot which family and which failure mode a question is really after, and how to move quickly through the handbook's welding and fastener sections under time pressure. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.